four masses shown are connected by rods, which was supposed to find the coordinates of the center of mass. And then find the moment of inertia of the axis that passes through mass A and is perpendicular to the page.
So it's rectangular, right?
Mm-hmm.
This
Looks
one's
like a
A.
square. But
Oh, 10 centimeters and 8 centimeters, so it's close to square.
where's the 10 centimeters?
Just
Oh,
around,
right there.
yeah. Right.
So we know this is, they said our y and our x here. So if I were to set this up, and we're trying to find, so for the x, bless you,
Thank you.
I would think that we would do, would be 100 grams times 0 plus 200 grams times 0 for the x, plus 200 grams times 10 centimeters, plus 200 grams times 10 centimeters, all divided by 246, 900, or 700.
Alright.
And for my x center, for my y, I would have 100 times 0 plus 200 times 8 plus 200 times 0 plus 200 times 8
Alright.
divided by 700. Okay. That's easy enough. But then when it says find the moment of inertia about the x-axis that passes through A and is perpendicular to the page.
Oh, through about an axis.
Mm-hmm.
So it passes through A and it's perpendicular to the page, which means it would go like this.
I guess.
So just like on that triangle one,
Yeah.
our axis that it was rotating about would be like that. Be sticking out of the page through the center.
Okay.
So they're asking an axis that's perpendicular to the page, so it sticks straight out of the page, and it passes through A.
Mm-hmm.
So this is the point that it rotates around.
So in order to find the moment of inertia, we have to take the summation of the masses times radius squared. And so the trick is to find the radius.
Mm-hmm.
But, okay, so here's my question. So we'll have mass 1 be the 100 grams.
Yep.
That's going to be 0, so we don't need to include it.
Yep.
B is the 200 grams.
Uh-huh. So you'll have, for B, you'll have 0.2 kilograms. What's your radius?
I want to say 8.
Yeah.
But it seems like it would be 8 or 4.
So what would make you think it would be 4?
No, it would be 8
Mm-hmm.
because it's connecting it.
Yeah, if you just ignore all the rest of this stuff, you just have this rod sticking up, then it'll rotate at 8. The radius of that circle would be 8.
So it would be 0.08 meters.
You
Right?
square that?
Oh, squared, great. And then that's plus, and then for C, we have 0.2 kilograms times, we will have to find, I would say we would take the magnitude, so 10 squared plus 8 squared, square root,
Yep. So you're just finding this distance.
Mm-hmm.
So 0.1 squared plus 0.08 squared.
Oh, thanks for reminding me about that. 0.08 squared, yeah.
And then
That's all squared.
square that.
So that should just get rid of the square root. And then that's going to be plus, we're going to have D, which is 0.2 kilograms, times 0.1 meters squared.
All right.
And that's equal to our moment of inertia.
Mm-hmm.
That's not too bad.
Mm-mm.
This stuff makes sense. I know where I'm orienting about.
So you add all those up, and then, oh, okay, that's all it asks. So sometimes they'll have you do other things. Your center of mass will end up being kind of out here, right?
Because that's where we're heaviest.
Yeah, since you've got this 100 grams, it'll be out further away. But sometimes they'll have you find the moment of inertia about the center of mass. And then you have to do some, I don't think they actually have you do that in any of the problems you'll have this semester or anything. But you could do it. You just have to take this length and this length and this length. This is the right triangle. So you know these two lengths, you just be able to find that one right away. Same thing over here. Take those two lengths, find that one, and you just do the same thing that you've been doing.
Cool. Well, thanks.
Actually, the center of mass, I think, is where it will have the least moment of inertia. It's easiest to spin something about its center of mass.
Right, because that's how ballerinas go on their toes.
Mm-hmm.
Is their center of mass is on the tippy toes of their feet.
Yep. Have you done any cool, because rotational kinetic energy is a really cool concept, but you can do some pretty cool things with it, just like demonstrations. I don't know if you've done any of them in class.
Mm.
But if you have somebody standing on like a spinning, like a lazy Susan, and you spin them and they have weights in their hands, and then they put them out, they'll slow down, and they put them back in and they'll speed up.
That's
Put
the
'em out,
rules of
slow down.
a ballerina, because
Yep.
like
Or like ice skaters and
when
stuff.
you have your leg out, you go slow. When you bring it in, you go faster.
And the cool thing is, you'd think that you could slow down by moving your arms out or your leg out,
Mm-hmm.
but then you wouldn't speed back up when you moved them back in, but you do.
You do.
It's pretty cool.